The 10 trillion solar mass scaffolding. The cosmic web contains 10 trillion times more mass than all the stars in the observable universe combined. While we spend our time looking at galaxies, they are actually just the bright foam on top of massive, invisible waves of dark matter. For decades, this infrastructure was a mathematical necessity that we simply could not see. But as of May 2026, the James Webb Space Telescope has finally provided the direct visual evidence required to confirm that the universe is built on a specific, rigid blueprint. This map does more than just show us where things are. It confirms that our fundamental understanding of how the universe grew from nothing is actually correct. And the method used to find these threads involves using the brightest objects in existence as simple backlights. Auditing the Lambda Cold Dark Matter model. Galaxies do not just float randomly in a void. They are tethered to a structural spine called the Lambda Cold Dark Matter model. This theory predicts that dark matter collapsed into long filaments first, creating a gravitational trap that pulled in enough hydrogen gas to ignite the first stars. If Webb had found galaxies scattered like buckshot instead of arranged in strings, our entire understanding of gravity would have collapsed this year. Instead, recent data confirms that galaxies are behaving exactly like beads on a string. This is a massive win for standard cosmology, but it creates a new engineering problem. If the Webb is this precise, we have to explain why some filaments are stretching faster than the expansion of space should allow. The structural integrity of the early universe depends entirely on the Aspire program findings, the 3 million light-year thread. In the last 30 days, the Aspire mission team released a map showing a filament 3 million light-years long, anchored by 10 distinct galaxies. This is not just a bunch of stars in a row. It is a physical bridge of gas and dark matter that existed when the universe was less than 1 billion years old. Think of it like finding the original steel rebar inside a skyscraper that is still under construction. By observing how light from distant quasars is absorbed as it passes through this bridge, astronomers have measured the density of the Webb itself. This confirms that the dark matter scaffolding was already mature and rigid, much earlier than previous models suggested. But detecting these threads requires a specialized light source located billions of light-years behind the target. That is where the Lyman alpha forest comes into play. Using quasars as cosmic lighthouses, mapping an invisible web requires a lighthouse. Webb uses quasars, which are supermassive black holes devouring matter so fast they outshine their entire host galaxies. As the light from a quasar travels toward Earth, it passes through the hydrogen gas that clings to the dark matter filaments. Each cloud of gas leaves a specific fingerprint in the light spectrum known as the Lyman alpha forest. By analyzing these fingerprints, we can tell exactly where the scaffolding is thickest. Some theorists argue that this web is far more clumpy than the smooth filaments predicted by our current simulations. If the web is too chunky, it suggests that dark matter might interact with itself in ways we haven't accounted for in our physics. This tension between the map and the model leads us to the ultimate signal under the noise. The signal under the noise. The recent Aspire maps and the detection of the 3 million light-year filament prove that we are no longer just guessing about the large-scale structure of reality. We are now auditing the blueprint. This validates the Lambda Cold Dark Matter model by showing that dark matter scaffolding was the primary driver for galaxy formation, effectively ending several competing modified gravity theories that gained momentum in the early 2020s. For anyone tracking the evolution of the cosmos, this means the mystery has shifted from what the universe is made of to how precisely those filaments are shaped. We now know the skeleton is there. The next step is measuring how much it is vibrating under the influence of dark energy. This transforms cosmology from a descriptive science into a structural analysis of the vacuum itself. Watch for the full data release from the Pearl survey later in 2026, which is expected to map the thickness of these filaments across 5 different epochs of cosmic time. We are finally seeing the bridge, not just the islands. Subscribe for more.